under Pieter Abbeel, and he's also worked in OpenAI before. And like everybody needs a reward in life, he will teach you how robots can also want to always get that and get something done. And the fun part is that when he started out working on deep reinforcement learning in India, he did not have GPUs. So he basically stole time from a cluster of people playing video games and started his research there, and now is making a lot of strides. So please welcome Aravind Srinivas.
Thanks for the introduction. So I'll be talking about work that we've done at Berkeley last year called Universal Planning Networks. This is joint work with Sergey Levin, Pieter Abbeel, Chelsea Finn, and Alan Jabri. Does this work? Doesn't work. Okay, thanks. So we've seen a bunch of successes in deep reinforcement learning, starting from the Atari games in 2015 and some control environments, Go, and this is Dota. Actually, right now, as we're speaking, the StarCraft live event is going on, and it seems the DeepMind bot's winning. It's already won the first 3 games, so that's another success. So almost all of these successes have relied on having very good reward functions. So all of these successes have relied on having reward as part of the representation learning problem, where the deep network is trained to optimize a bunch of rewards. So in this case, in the breakout game, you're optimizing the score that's highlighted in the top. But the truth is, in the real world, you're not going to get rewards very easily. For instance, this child who's trying to pour water onto the glass, it doesn't really have a reward as the amount of water on the glass that's poured yet. There are no sensors to track the amount of liquid in the glass and so on. So how do you actually get agents to perform tasks like these without a trivial way to engineer the reward functions? So in this case, the only way to solve such problems is to learn the right representation and try to achieve some goals. For instance, if the goal was to have the image, say, with a glass complete with water, you learn an execution to match that particular goal image. So you need to learn deep learning representations for goals and rewards. Pixel level objectives for doing this are very problematic. The reason is, for instance, if you try to match all the pixels for the goal image with the control problem, let's say you want to match every single pixel to the goal state, that's going to be really, really hard. It's a very sparse reward. You could also have objectives that try to optimize the Euclidean error between, for instance, you could try to minimize the distance between the goal image and the indicator image in terms of the metric space. And that's not really going to work well either, because it's not robust to translations. So minor artifacts, some translations in the goal image, those are going to be problematic as far as optimizing that reward is concerned. So if you train an encoder that's trying to do pixel reconstruction, like say an autoencoder or a variational autoencoder, you're going to encode all sorts of noise in your representations. For instance, you can have like these broken glass. So let's say you're trying to have rewards so that you don't have to break glass on a dining table. Then your autoencoder or variational autoencoder is going to encode all these kind of noises, which you don't really want to be part of your representation. So, or let's say there's this noisy TV channel problem where you just switch on the TV and you get a lot of noise when the signal is not right. So if you just train a deep network to minimize reconstruction error in the pixel space, these representations are really problematic. So representation learning targeted for control and planning is really an important problem to figure out. So that's what I'll be talking about. So what kind of representations do we actually need? We want representations that can be plannable in the sense you should be able to plan using the representation to achieve a goal image. And you want them to support goal-directed behavior, basically. So another way is to use generalizable representations. And you want representations to optimize directly for what you care about, that is, for achieving your goals. And so I'll get to this, what it actually means soon. So the key idea is we are going to optimize for representations that support planning. And I'm going to talk about the architecture called UPN, Universal Planning Networks. So the way it works is as follows. You're given an initial observation and a goal observation. So just a simple example where this quadruped, four-legged quadruped has to go to the goal image, say the blue location, and the actual optimal trajectory is highlighted on the right. So those are given in terms of raw pixels, and it has to plan this trajectory using these raw pixels. So how do we learn plannable representations here? The way we learn it is we want to learn representations such that if you run a gradient descent optimization on it, if you run a trajectory optimization in the latent space, whatever the algorithm outputs should be grounded with the true optimum. And we get the true optimum using an expert trajectory. So we have an imitation learning loss in the outer loop, and that's backpropagated through the planning algorithm that's highlighted in the block. So the way I'll outline this is I'll explain the architecture and the benefits that come from it and how it's being used to construct reward functions. So here it goes. So initial observation. And you encode it in the latent space. And you have the goal observation that's also encoded in the latent space. So you can start off with an initial sequence of actions that you think will get you to the goal from the current state. And you run a forward model in the latent space. This forward model is actually being learned. So you start off, you imagine what's going to happen if you execute all these actions. So you keep running it. You run it for t steps, and you think about the final latent state in the end. That's the goal state. And you compare it with the latent state of the actual goal that you have to reach, and you take the difference and you backpropagate this error back into your actions. So you're backpropagating to your actions, updating it again, and rolling out the next sequence of actions. So this happens for several iterations. So this way, you get a very chained computation graph. This is like a recurrent neural network that keeps unrolling your actions, your current actions that you think are optimal, and you keep constructing better actions that way compared to the goal state. Now you want to make sure that whatever this block outputs is optimal, that it actually ends up achieving the goal. And the way you do that is by using the imitation learning loss in the outer loop. So you assume that you have a bunch of trajectories that are given to you from an expert. So you have this module that just runs gradient descent in the latent space onto your plan, and you learn to learn that module, basically. So it's like a meta-learning construction. So this way, you're optimizing for planability explicitly, because the internal module is basically a planner. And this is what I actually meant by optimizing directly for what you care about, because at the end of the day, what you want is a representation such that you can achieve goals. And this way, you're explicitly optimizing for that. You're not assuming that having a variational autoencoder or certain other self-supervision objectives hopefully give you the right representation. So in summary, this is a goal condition policy architecture with trajectory optimization embedded inside it. It's a completely differentiable module, so you can learn with gradient descent. And the reason it's good is because you hope that this kind of model-based reasoning can generalize better than just naive imitation learning. So here are some experiments that kind of support this hypothesis. So we want to see if we can learn effective imitation given a bunch of trajectories from the expert compared to conventional methods. So here it goes, some learned policies. So let's say the first case is just a simple point mass that will be given a goal image on the right, and it has to just plan a sequence of actions. Note that the tasks are constructed such that you need some kind of planning behavior where you have these obstacles, and so it's not a conventional reaching task where you can just learn simple RL or imitation policies. And note that given sufficient number of demonstrations, naive supervised learning will work pretty much as well as this architecture, because with enough data, like you can have simple architectures work well. But the inductive bias helps in the regime where you don't have sufficient number of demonstrations. The more interesting question we wanted to know was whether not just that it is more sample efficient in imitation, but whether you can take something from this representation and use it for something else. That's what I meant by generalizability. So we wanted to see if this planner can be useful at test time for more than what it was trained for. Let's see. So here we want to see if the number of steps you use to internally plan, the number of planning iterations, can be extrapolated at test time. So even if you train for, say, 40 planning steps, if you just at test time increase the number of inner loop planning steps, can you get better behavior? And it turns out yes. So the red line says you plan 40 planning steps, and the top red line is with more demonstrations. And you can see that even with 20,000 demonstrations, as you keep increasing the number of planning steps, you can match the performance with more data. So that means that it's learning some kind of useful inductive bias that can be exploited at test time. The final thing that we wanted to know was whether we can go beyond imitation learning. So we are learning this gradient descent planner, and we hope that it can be useful at test time. So the thing that we want to exploit at test time is the reward metric we are learning in the planner loop. So we wanted to achieve goals. So what if this planning metric itself can be used as a reward to train a model-free RL algorithm on new tasks? So that's the question we wanted to learn. And some supporting visualization is that in the case of this block reaching the obstacle reaching task, the metrics that you learn are not Euclidean. They are actually aware of the obstacles. So hopefully, you can transfer such representations to new tasks. For instance, you can learn a representation for a point mass and transfer it to another morphology like an ant, or you can learn it on a 3-link creature, transfer it to like a 4-link or 5-link creature, as long as the semantics of the task are the same. So here's how it works. We train on demonstrations from 3- and 4-link creatures, and you construct that metric function that you learn, and use that as a reward to optimize a new 5-link creature for which you never had any demonstrations. Similarly, from a point robot to an ant, or even a humanoid, because the semantics are the same. So you can you can also optimize much longer horizon tasks this way. So the key takeaways are that we propose a way to do effective goal-directed visual imitation and transfer task-related semantics to new tasks, and also the fact that planability is a good criterion to think about in general. There are also other notable work in this space, goal-directed tasks, time contrast networks, contrastive predictive coding, discern. I think Jeff is also going to talk about how to use it in exploration, which I'm very excited to hear. And yeah, thanks to my collaborators. You can check out the code on GitHub. Thank you.